Hello guys, welcome back to my YouTube channel. Myself Kiran Gowda. I am currently pursuing in BE first year in Sri Venkateswara College of Engineering. Today my subject is about engineering mathematics for CSE stream and my topic is vector calculus. Vector calculus, an introduction. Explore the fundamentals of vector calculus, a powerful mathematical tool for analyzing and understanding the behavior of multidimensional systems. Dive into the core concepts and their real-world applications. Scalars and vectors. Scalars are quantities that have magnitude, size, but no direction, like temperature or mass. Vectors, on the other hand, have both magnitude and direction, like vectors are force. They are represented by arrows. Vectors can be added, subtracted, and multiplied in various ways to describe physical phenomena. Vector algebra is a powerful tool in physics and engineering. Vector operations: addition and subtraction of vectors, combining two or more vectors by adding or subtracting their corresponding components to obtain a resultant vector. Scalar multiplication: multiplying a vector by a scalar, a real number, to change its magnitude while keeping its direction constant. Multiplication of vectors: the dot product, scalar product, and cross product, vector product. Two vectors resulting in a scalar are a vector responsible. Dot product and cross product. Dot product. The dot product, also known as the scalar product, measures the projection of one vector onto other. It provides a way to calculate the work done by a force or the power generated by a moving object. Cross product. The cross product or vector product results in a vector that is perpendicular to both input vectors. It is useful for finding the normal vector to a plane or calculating torque and angular momentum. Geometric interpretations. The dot product can be visualized as the product of the magnitude, the cosine of the angle between them. The cross product gives a vector magnitude is the area of the parallelogram formed by the input vector. Vector functions and differentiation. Explore the fascinating world of vector functions where variables are represented as vector quantities. Learn how to differentiate these functions, uncovering the intricacies of their rates of change and gradients. Dive into the mathematical foundations that govern the behavior of vector. Valued functions, equipping you with the tools to analyze and apply them in vectors, engineering, and scientific domains. Gradient, divergence, and curl. Gradient. The gradient of a scalar field represents the direction and the rate of change of the field. It points the direction of the steepest increase and its magnitude indicates the slope. Divergence. The divergence of a vector field describes the density of the outward flux of a vector field from an infinite volume around a given point. It measures how the field diverges from the point. Curl. The curl of a vector field is a vector field that describes the rotation of the vector field in the vicinity of a given point. It measures the tendency of the field to curl or rotate around the point. Visualization. Gradients, divergence, and curls can be visualized using vector field plots, contour plots, and other techniques to gain intuition about the behavior of vector fields. Line integrals and surface integrals. Line integrals evaluate the integral of a vector field along a curve. This captures and work done by a force field or the flux of a current through a wire. Surface integrals compute the integral of a scalar or vector field over a surface. This represents the total flux of a vector field through a surface. Applications. Line and surface integrals have numerous applications in electromagnetism, fluid dynamics, and thermodynamics, allowing us to analyze properties like circulation and flux. Fundamental theorems. Green's, Stokes, and divergence. Green's theorem relates line integrals to area integrals in the plane. Stokes' theorem relates cutoff vector field to a vector integral. Divergence theorem relates divergence of a vector field to a volume integral. These fundamental theorems in vector calculus establish powerful connections between different types of integrals, allowing you to simplify calculations and gain deeper insights into the behavior of vector fields. They are essential tools for analyzing and solving a wide range of problems in physics, engineering, and mathematics. Applications of vector calculus. Fluid dynamics. Vector calculus is essential for modeling and analyzing the complex behavior of fluids, such as the flow of air around an aeroplane wing or the circulation of blood in the human body. Electromagnetic theory. The concepts of gradient, divergence, and curl from vector calculus are fundamental to understanding electromagnetic phenomena, from electric and magnetic fields to Maxwell's equations. Gravitational fields. Vector calculus is used to model the gravitation fields of celestial bodies, allowing for the prediction of planetary and satellite orbits as well as behavior of black holes. Thermodynamics. The concepts of vector calculus such as the divergence theorem and Stokes theorem are essential for understanding the analyzing heat transfer. Practice problems and exercises. Applying fundamental concepts, solve a variety of practice problems that reinforce the key principles of vector calculus, such as vector operations, differentiation, and integration. To real-world scenarios, explore how vector calculus can be applied to solve the problems in engineering, physics, and other scientific domains through carefully crafted exercises. Computational exercises. Implement vector calculus algorithms using programming languages like Python or MATLAB to gain hands-on experience with the computational aspects of the subject. Conceptual understanding. Engage in discussions and answering questions that challenge your understanding of the underlying concepts and their applications in vector calculus.